started talking about isomers, which obviously, or finished talking about isomers and different types, which obviously is in the lab for today. We're now going to talk a little bit about bonding and sort of how electrons are distributed in complex ions in the presence of these ligands. So, as you may remember from bonding, a lot of times we do form hybrid orbitals. Dare I say that's like an SP, an SP2, an SP3, SP3D, SP3D2, right? The hybrid orbitals are related to the electron pair sort of geometry in traditional sort of VSEPR, and that is basically two letters, so that's like linear, right? That is three letters, which is three electron pairs. That's like trigonal planar. That's four, and that's like tetrahedral. That is a little trigonal bipyramidal with five and a little octahedral with six. By the way, if you don't know how to assign hybridization, it's a relatively straightforward sort of deal. You could kind of do this as the easiest move. And you count up electron pairs just like everything counts as one, and you basically just count off the electron pairs. So if you had like a carbon-carbon double bond, right, and we look around, say this carbon, that is one electron pair, two electron pairs, three electron pairs, one, two, three, that is sp2 hybridized. It's the easiest way to do it. Now, the interaction in terms of complex ions, though, can be viewed as we've been talking about, sort of a Lewis acid base situation where we're accepting electrons into those d orbitals. The hybrid orbitals used by the metal does depend on the ligands that are attached. It can take a few different sort of geometries in terms of the ligands that are present. Also, the coordination number plays a big role in terms of sort of its hybridization and geometry as well. So here's our really octahedral geometry here. And basically you got 1, 2, 3, 4, 5, 6. 6, much like 6 electron pairs, is octahedral, right? So that again sort of relates to each other. Here are a few common geometries that we see with complex ions. Tetrahedral, right? We have square planar. These are also coordination numbers of 4, basically. Here is a coordination number of 2, which is more of a linear geometry, a SP sort of hybridization. And obviously, since this guy is square planar, that's the expanded octet. So again, it is our sp3d2 versus our sp3, which is our non-expanded octet that happens here in our tetrahedral. So the geometries that relate to sort of our coordination numbers and most commonly that you come across are really these here. If you have a coordination number 2, typically you will have more of a linear structure in terms of how those sort of ligands place each other. It's kind of the same idea as when you have two electron pairs, right? Everybody tries to get as far away as possible from each other. So they end up on opposite sides of a straight line, right? 180 degrees apart. With a coordination number of 4, again, you can have one of two sort of geometries that go with that, more of a tetrahedral or a square planar. We just saw the square planar when we were talking about those isomers, the cis and trans isomers. And also coordination number 6 is going to give you that more octahedral arrangement. And that was also what we saw as well a little bit when we looked at the cis and trans isomer, where we had the chlorine above and below the plane in the middle, right? So that kind of 6 ligands attached. Typically speaking, with coordination compounds, they will tell you a lot of times this is taking on tetrahedral geometry, or this is taking on kind of like a square planar geometry. So they'll oftentimes give you sort of that information, sometimes in the problems as you go through it. So when we're talking about the metal that's in the center of your complex ion, because this is a transition metal, typically we're into our d orbitals, and there are 5 different d orbitals, and these are the 5 different d orbitals that are present. Now, in the absence of any ligand that's present with the metal, all 5 of those d orbitals are all going to, for example, if they're 3D orbitals, they're all going to be basically at the same energy level. So every single one of those 5 individual d orbitals that make up the d subshell will be basically equal in energy. What happens though when we actually get some ligands coming in is there's actually a difference in the energy level of these d orbitals. So they will not all be at the exact same energy level. And that affects how electrons will sort of occupy the orbitals. As you hopefully know, right, electrons go in lowest energy first, right, until that's filled, and then go the next lowest, right, until that's filled, the next lowest. So they always fill sort of electrons lowest to highest until the lowest are filled. And what happens, as we can see here, for example, is these d orbitals, once we start getting some ligands involved and starting to bind, there's actually what's referred to as a splitting of the d orbitals. This, by the way, what we're looking at is a coordination number of 6. This is the octahedral geometry splitting that we're actually looking at here. And what you can see here is we get 3 lower d orbitals in terms of energy, and we get the xy, the yz, and the xz there. And we get all of our squared d orbitals going up higher. And the energy difference between the higher and the lower pair of d orbitals in this case is what is referred to as the crystal field splitting. It is sometimes abbreviated with the little delta symbol. You could calculate that like normal by taking E is equal to h times the frequency. That is Planck's constant. 6.63 times 10 to the minus 34 joule seconds. That is the frequency, and reciprocal seconds are a hertz. And you can actually calculate the difference here. And what happens in terms of the arrangement of the electrons in the metal based on the splitting is, for example, let's just say that we had 4 d electrons into these orbitals. With this type of splitting, what's going to happen is this. It will start to fill the lower energy first with 1 at a time, just like normal. And now with the 4th electron, it has to kind of make a decision. And the decision is this: is the difference in energy between the lower energy level and the higher energy level d orbitals too big? And if it's a really big splitting, what will actually happen is the electrons will go, no, thank you. I'm just going to go down here first. And it'll actually pair up down at the bottom. Now, if you had sort of the same idea here and this splitting wasn't necessarily as big, we just have more of a smaller sort of crystal field splitting, what would happen is our electrons would go this way and decide, hey, that's not too bad. We'll just go up here and kind of feel like normal. And depending on how big or small the difference is between the d orbitals, it will allow the electrons to sort of occupy the different orbitals, either a little bit more lower or a little bit higher. This gives us some differences in the number of unpaired electrons. As you can see in my example on the left, I have 2 unpaired electrons. My example on the right, I actually have 4 unpaired electrons, right? And that's what's referred to as paramagnetic, right? A lot of unpaired electrons. This is what creates what is sometimes referred to as a low spin complex and a high spin complex. A low spin complex would be the one here on the left in my example. It has less unpaired electrons. And the high spin complex would be the one on my right that has a lot more unpaired electrons. So the way that we could do this is obviously we can promote electrons by adding just a little bit of energy. And because the splitting may not be all that big, we could actually promote some electrons up there. As you know from being professionals in this business, we take the maximum wavelength, right, for our absorbance here. And the color that we actually see is the complementary color, right, to the wavelength that's being absorbed, right? So when we see a red solution, the light that's being absorbed, like in our spectrophotometer, is not red light. It is the complementary color, right, to red. And that's why you set the wavelength there. As I mentioned, you could actually calculate the crystal field splitting by using the same old 200A equation that you learned in week 2. Maybe it was week 4. I don't know, but somewhere early on. That also brings us to the other equation that you might remember from there, which is C is equal to the wavelength times the frequency. C is the speed of light. I roll with 3. I don't know why people like to use 2.997, but I'm going to go with 3 because I feel like rounding. Or some people like 2.997 times 10 to the 8 meters per second. That is the wavelength, right? Our lambda there. And wavelength is usually in meters in this case. And that obviously is our frequency, which is again reciprocal seconds. Now, the relationship here, as you may know, is these two equations can be kind of put together, right? And that is because the frequency is equal to the speed of light divided by the wavelength, which means that E in this case would be hc over the wavelength. So if you know the wavelength of light here that you're shooting there, you can figure out the crystal field splitting, or if you know the frequency of the light, you could also figure out the energy difference between the lower d orbitals and the higher d orbitals in this particular case. Any questions on that there? Clearly, in each of these cases, wavelength needs to be in meters for everything to cancel out correctly, right? Otherwise, you're not going to cancel out correctly. So just to show you an example of this problem, which I think is actually worked out, so we'll just kind of go through it to explain where all the numbers kind of came from. The absorption maximum of a complex ion of our cobalt that we saw earlier there, that we now know is hexamine cobalt 3 ion, we want to name it, occurs at 470 nanometers. What is the color of the complex? And what is the crystal field splitting? So the color of the complex, obviously, it's absorbing at 470. So it is absorbing at 470, which is here. Again, the color that we're going to see on the color wheel here is the complementary color. I guess red wasn't the best choice there. So we will see over here. So it will appear orange to us. Again, that is why when we, for example, had a red solution, we set our wavelength in this area, right? The green, which is complementary to it. So that is, again, how you would determine the color of your complex ion based on where it absorbs. Here we could calculate our energy of our crystal field splitting by using the equation with the wavelength. Again, 1 nanometer, right, is 10 to the minus 9 meters. So you do have to do that conversion, which is what this is down here. That obviously is our speed of light, which is c, and that is our Planck's constant, which is h. Putting that in there, that gives us basically a energy split of 4.23 times 10 to the minus 19. Although it is never sort of written, that is per atom, basically. And if we want it in kilojoules per mole, we can use our friend Avogadro's number, right? Which takes us from atoms to moles, right? And that is what that conversion is there. We go Avogadro's number up on top, 6.022 atoms over a mole. The rest of the number would be good too, I suppose, 23. And again, our atoms will cancel, and that will get us to our joules per mole, and then obviously converting it into kilojoules per mole. 1,000 joules is a kilojoule, gets us to 255 kilojoules per mole. So basically, it's this equation, then multiplying by Avogadro's number, converting it to per mole, gives us our number here. Any questions on that calculation there? Okay. So how do we know if we're going to get sort of a large split in the d orbitals or a smaller split? And it has to do with the ligands that are present. And certain ligands are what are referred to as weak field splitters, and certain ligands are referred to as strong field ligands. And what that means is if it's a strong field ligand, you're going to get a big split in energy, dramatically drawn here, between the lower d orbitals and the higher d orbitals. If you have more of a weak field, you're going to get a much smaller difference between those lower energy orbitals. and the higher energy orbitals in this case. And what that's going to do again in this situation is if you have more of a weak field, it is going to fill like normal. It will go up there. And by the way, once it gets to the top there, it will come back down and start filling up down on the bottom as well. Here in a stronger field, it's going to go across and go, no, thank you. I'll just come this way. And it will only be forced to go up there where there is no more room left, basically, and it has to go up there. Again, we're going to get a lot more unpaired electrons here in a weak field versus, I'm sorry, a lot more unpaired electrons in our weak field versus our strong field. And in this case, this is going to give us a more high spin complex. And this will give us a more low spin complex, as we're going to get a lot more paired up electrons. Again, a lot more diamagnetic, which we have paired spin, versus paramagnetic, where we have kind of everybody going the same direction. Now, what happens in the middle? Well, I'll be honest with you. In the middle, it could go either way. And sometimes they will give you some information. They may tell you, hey, do this for the weak field, or do this for the strong field, or do this for the high spin complex or low spin complex. So sometimes in the middle, they'll kind of give you some information if you're not sure. And then if they don't give you any information, sometimes it doesn't matter. So for example, let's just say I had something and I had my weak field here versus my strong field. Let's borrow the real boxes there. I'll do this way. And let's just say I only have 3 electrons total that I need to distribute. So no matter which one you do, it's all going to come out the same, right? Because nobody's going up anyways, because you don't have enough electrons to get up there. So there are some situations where it won't make a difference. If you kind of do it high field, weak field, it'll basically be the same no matter which way that you go. Any questions on that there? All right, so here's some examples. Just talk about this. And this is where we were talking about electron configuration comes into play. Let's take our nickel here and our Br6 and our -2. So in this case here, that's -1 for our Br. And there's 6 of them, gives us a -6. Overall, it's a -2. That means my nickel here is actually a +4, right, in this particular case. Again, if we look at nickel on the periodic table there, that's 28, which gives us our argon 4s2 3d8 in this case. Our nickel with a +4 charge, as we drew, I think did earlier on, we're going to lose our S's first, and then we're going to lose a couple out of here. And this would give us our argon 3d6. So we're talking about the nickel here, which is our metal in our complex ion. And we're talking about distributing these 6 electrons into those d orbitals. This, by the way, is a coordination number of 6, which would be our octahedral splitting that we've been looking at in this particular case. So when we look at this, we're going to get this splitting that's going to occur in this case because, again, it's octahedral. So we'll have those 3 guys on the bottom, the other 2 up on top. So what we have to decide now is Br and where Br lies. And we look at Br over here, and it's a weak field. And what that means is, and I'll just use these boxes since they're here, since the Br is weak filled, we're going to get a small crystal field splitting. So the difference between the upper d orbitals and the lower d orbitals in terms of energy is not that big of a difference. And that means that when we go to distribute those 6 electrons, we would expect it to do 1, 2, 3. Because the crystal field splitting is not all that big, it will come up here and go 4, 5, and come back down and go 6. That would give us how many unpaired electrons in this case? Give us 4 unpaired electrons. And this is going to be considered probably a high spin complex because we have a lot of unpaired electrons in this case, right? Any questions on that one there? Now, if we look at, let's do this guy here, the nickel with our En3. Coordination number here is 6 because En, as we talked about, is a bidentate ligand, right? So you get a 2-for-1 on that deal. That also means that this should be our octahedral splitting, just like we had before. En is 0. This will also be a +4 charge in this case. That also means that the nickel in this example will have the same 6 electrons that it needs to distribute. The difference here is when we look at En, it's closer to a strong field, which means when we do our splitting of our 3 lower d orbitals and our 2 higher d orbitals, this is going to be a large splitting that's going to occur. The result of that is when we go to distribute our electrons, when we get down to here, it's going to decide, no thank you, because that's too big. I'm just going to come down here. And in this case, we end up with how many unpaired electrons? 0 unpaired electrons. This would be considered a low spin complex, as you have a lot more paired off electrons than unpaired electrons. Any questions on that there? Okay, so why don't you try these two here? Why don't you do these guys and we'll do this as a weak field. We'll do that guy as a weak field, and this one you can decide yourself for a top one. Iron is 26, I think, still. You haven't changed it, I hope. All right, so what I want to know is I want you to draw the crystal field splitting diagram. I want you to determine the number of unpaired electrons as well. And is it high spin or low spin? Why not? We'll do that. High spin, low spin. For obviously these guys here. Wrong spot. I meant for that to be out there, by the way. That would make a little bit more sense. Okay, that'll look right. Okay, look here, and we'll start with the one I meant to write weak field on, I think. All right, we'll do this one as a weak field. So in these cases here, we have Cn minus, which is -1. That's a -6 for all 6. We only got -3 left over. So our iron is +3, and I believe it's also going to be +3 in this guy as well. That's going to be a -1, and there's 6 of them, gives you a -6. -3 gives you a +3. This is a coordination number of 6, which gives you the octahedral sort of splitting that we've been looking at. Iron is 26, which means +3 is 23. So that's going to give you an argon 3D, what we got there, 5, I think, if I'm not mistaken. And that is for our iron with a +3 charge in this case. Now, these are the 5D electrons that we need to distribute. Since I did weak field on this, our 3 lower guys and our 2 higher d orbitals are not going to be very big. It's going to be a small splitting that's going to occur. So as we go and distribute this, 1, 2, 3, it's going to decide that's not too bad. We'll just go upwards here. And in this case, we will end up with 5 unpaired electrons in this case, and that's a high spin complex here that we get with a weak field. Any questions on that there? Coming to here, which is also a +3, gives us the same 5 electrons. But when we go to our Cn minus, I'm so backwards on this problem, I don't know why. We're looking at Cn minus on the second one there. And that is going to be a strong field, which is going to give us a larger splitting that's going to occur. So in this case, dramatically drawn here, much larger here. There you go. Now we're going to distribute our electrons, 1, 2, 3. They're going to decide, no, thank you. I don't want to go up. We will go down first here. And at this point, this will give us 1 unpaired electron. And since we only have 1 unpaired electron, that would be considered a low spin complex. Any questions on drawing it? Yes, ma'am. It has to do with the ligand being present and which ligand it is. So for example, this ligand here, we want to do it for the weak field. And the weak field means that the energy difference between the lower d orbitals and the higher d orbitals is not all that big. And it's not big enough to deter the electrons from just going in following Hund's rule, maximizing the parallel spin. So because it's relatively small, it will go through and go, that's not too bad. That's not way up there. It's not too big of a hill. So we'll just go up there and feel like normal. Over here with this guy, this creates a larger crystal field splitting. So there's a bigger energy gap distance between the lower d orbitals and the higher. And in this case, it's going to be too big of a gap for them to go up first. They much rather kind of hang out there in that lower energy. The only way they will go up there is if they're forced to, like they have no more room on the bottom, right? All the vacancy is over there. You got to go to the next floor to get a room. They will have to go up there at that point, and that's why we end up that. So typically speaking, if you have a small crystal field splitting, you will end up with a lot more unpaired electrons because the difference in those energy levels is not that much. So everybody's just going to kind of follow Hund's rule. With a larger crystal field splitting, you're going to get the idea of, I don't really want it to spend that much energy to try to get up there. I'm just going to go lower first. It's just kind of the easier pathway. And you'll get a lot more paired electrons, a lot more diamagnetic than paramagnetic, which is unpaired electrons. Other questions? All right, cheers. So that is, of course, Melvin the fish. Never know where Melvin may show up. A little old school throwback for some of you that had me. He might show up on Thursday. So Melvin the fish, in case you're asked that question. All right, so here we go again with our iron and our guys that we just did, again, giving us our high spin complex, our low spin complex, more paired electrons happening. Here's basically for octahedral, the different arrangements. This is all high spin, and again, a much smaller splitting that's occurring between our d orbitals. Larger the splitting, again, more low spin happening, more pairing up before they try to travel up on top. Again, unless they're forced to. At this point, as you can see, there's no more room for this guy. He's got to go up there because there's nowhere else for him basically to end up. Now, let's talk about some other geometries. With a coordination number of 4, you could get tetrahedral geometry. And you also get the splitting, but it's kind of upside down versus what we just saw in octahedral. Bless you. So the 3 that were on the bottom for octahedral actually end up higher in energy, and these guys actually end up lower in energy. It works the same way. If we were to fill this, we would fill these guys first, and then they would have to make the decision to go up or not go up. And it's really the same sort of idea. If you have a small crystal field splitting, they will go up and kind of feel like normal. If you have a larger one, they're going to fill the bottom first and then go up and fill one at a time. By the way, these do go into these orbitals just like normal electrons, one at a time, right? And then go and pair up if they need to pair up. Now, with a coordination number of 4, you also can get a square planar complex. That looks crazy. But there it is. Same idea, though. Obviously, a lot more splitting happening here. And again, the filling would work the same depending on, the energy difference between kind of your upper and your lowers here. And clearly, we don't want to be responsible for that because that looks very scary. So we won't do that. So you are responsible for tetrahedral, which is basically the opposite of octahedral, right? And the octahedral one that we've been talking about. So those would be the 2 that you would be responsible for the final exam, I guess it would be at that point. So octahedral splitting and tetrahedral splitting. Any questions? Yes.
That's where I get how many electrons.
Exactly. So what we were talking about earlier about writing electron configuration for ions, we're talking about the metal ion, which is a lot of times is that transition metal that's in the middle of the complex ion, and whatever the charge is on it. In these cases, it happened to be 3, and then we have that nickel that had a 4, and that you'd want however many d electrons that metal has in its ion state is what you would distribute through these orbitals. Yeah. Other questions?